Do the trending for EFL thing.
I was solving J like I got started pulling.
Oh my god, you're actually degen.
Gambling.
We get 7, 8.
I'm gonna keep sending it out of it. Yeah, go.
I mean, obviously, it was like an easier.
You want me to get started or?
I guess
Let's give it another. Like started like quarter past.
Last one around the 2 teams. I have one word. You have one word?
That's the really good XP. I don't
He needs some girl experience.
Oh wow.
And then he thought like he's
Is it
experience.
he's trying to like because basically what we
That's very-
exactly so he's trying to like just putting them together.
I don't know why like everyone like picks up the
Got it spot on.
Yeah, it just I didn't understand what Jarvis.
Like you were talking about problem A. Like I didn't see like the
Yeah.
problem diagram.
It took us so long.
Yeah, like yeah, as it turns out, like
Because a lot of
as I think about it, like the problem like literally is
the time in the test cases, like you can just add and subtract ones.
oh yeah, but that's not.
Everyone else just leave.
What was the mistake that
No, why didn't I?
No, they're like coming.
I think we're just going
Okay.
like plus or minus one, and it worked for some.
I was just like looking for a side.
Oh, we shouldn't count the root for some reason. We shouldn't count. Yeah, but we still count it in the end. It's like part of the.
Maybe.
We should definitely.
And then realized
Oh yeah.
that it was like between two terms.
Do you know something?
And then just like
Oh yeah,
yeah,
the-
figuring out the actual
Try.
yeah.
like it's like
We did that.
you know
Do that and
Which-
find the diameter.
We did end up doing.
It's a 2, right?
Yes.
And the diameter is just
What's the diameter?
we found the start,
the
which
two
is
nodes
like
which are the longest apart from each other.
Yeah, we did that.
terminal node of the longest string.
Yeah.
We did that in the past, so maybe it works. Wait, what's your
I don't
definition?
know how it works.
Like, how do you find your diameter?
It's like it's literally that there is a way to construct like a really long word.
Did you consider this?
You have that like you can find the longest.
Consider the case where there is two strings, one of which is the suffix, substring in perfect substring.
Right. I'm going to that both.
But like the fact that you can recurse on and just find it, already know that you
How do you find it? Like, You can't advertise our club. Yes, everyone jailbreaks.
I know this early I would not. Like,
It's okay, next contest we'll have a mirror, so you can join ACDL, it's kind of like.
Maybe
We did it.
We only have like
Yeah, that's what the AU is for.
Yeah.
Okay, well, I'm supposed to do.
yeah.
they're grandmasters.
yeah, that's because you suck at chess.
That's true. That's true.
That's true.
It's like a chess.
I actually don't know if you suck at chess, dude.
I don't know. You want to get?
I mean, you beat me.
Okay.
My brother's 1,000 rated, exactly.
Good for general. Yeah. I mean, you would probably reliably be average people.
What are you?
my just like
Yeah, we need to make we need to make it.
yes, no, I feel like I play below that right now.
Oh,
Just because gotta. You should have a game. Or it's hubris.
Oh, you let me know when you need the cannon event and I'll show up. No, it's all about timing.
What about timing?
Yeah, sometimes people need that cannon event. Sometimes it just destroys them without
Yeah.
effort.
I like to stand.
If you feel he needs that.
Yeah.
Yeah.
I don't know if it's like
that.
Nah,
It's not. It's
that's hubris.
Mine does those really bad. I just still hold it great.
You went for it.
I'm putting the really I was just doing something wrong.
I mean, you should definitely see like as like
Yeah. The input constraint for problem E was like,
Oh, this is.
Initially wrong.
yeah, but like.
I hate the new schema, by the way. Also, Corona is coming back.
Let me
That's the point. You know.
It has a phantom upgrade, right?
I think Phantom will be
Anything
like
further,
better than
like doing top sorts of fucking everything.
actual OOL.
Question mark.
Yeah.
Right? I think to me it makes sense that we
I like
make
that.
implements like that.
I wish them to.
Not
Actually,
get up.
Move me out of the deck.
I mean, like last week, now I'm kind of like,
Oh, yeah. The lower, like higher tier.
Yeah.
the problems were hard.
They were hard. We hit a brick wall right around that time anyway.
No.
You want you to.
I think that's the brick wall.
No.
I think the brick wall's like 3 years out of the wall.
This is the gimme question.
That was the pretty much yeah that was this I gotta say this is genuinely peak. That is peak working out.
Like 10 minutes.
I'm personally proud of how I had while you guys were working all day. And then I just went full high school working out on paper mode. And I found the mistakes.
Oh, bro, it's
Oh, yeah.
actually.
This was great. I knew it was. It's just needed someone to go down.
Yeah, exactly. I had to just, it's at this point, it's just
Yeah,
the
just-
calculation and just,
Figuring it out.
yeah, it's just going in.
Logic when you wrote that.
Yeah, you'll notice I'm updating like the hash map.
Okay, we can probably get started now.
That's me.
Hello, everyone. Yeah, welcome to the editorial for part 3. Good job to everyone who attended. This contest had some easy problems, some hard problems. It was good to see a lot of you doing lots of problems at the end. I hope that you all I think we're gonna see full folks here. Yeah, we had 7 teams full fold. All of them got gold. Very good. I think the average number of souls was roughly 4 to 5. We had about 80 teams in total, which was a much bigger turnout than we expected. So thank you all for your contributions. We're going to go through the solutions to the problem now. We're going to start from the easiest that the original problem setters devised, and then we can go through to the hardest. And contrary to what a lot of you guys did, the easiest problem that they thought was actually problem D, drag out duel. So you have a friend, a desire, and you're playing rock, paper, scissors with him. And you have some long string of your move, where the like character of the string is your move in the game, and you have some long string of the other person's moves, and you have to figure out whether you beat them or not. And this can be up to 10 to 5 games.
We have one-line solution.
What's that?
We have one-line solution.
You have a one-line solution? Yeah, this problem is certainly one-line solvable. Essentially, you just iterate through all the strings. You can pair the characters. If you have a rock and a scissors, or paper and a rock, or something else, you can essentially increment the count for desire versus the other player. And as part of the problem constraints, it's guaranteed that one of you will have more wins than the other. So once you process all of the characters in the string, all the pairs of the characters, you can figure out who is the final winner. Big win, you got that one. Next is problem B, building pyramids. So this problem is also fairly straightforward. Given a pyramid of some side length n, you have to figure out how many spheres are in the pyramid if you were to make a tetrahedron, of that size. Now, as you may know, a tetrahedron is made up of like equilateral triangles. So if you had a tetrahedron of height, I don't know, 3, then the bottom layer would look something like this, where you have a triangle of size 3, and then the next layer would look like that, and then the next layer would just be 1. And once you add these all up, you would get the answer for n equals 3. Now, if you were to actually try and manually count all of the balls in the tetrahedron manually, this is going to be too slow because it can be much larger than, I believe, 10 to the 8. However, we can use a triangular number formula here. So if you know that n equals 3, then the nth triangular number, the number of spheres in any triangle of some side length n, is n times n plus 1 or 2. And so you can simply calculate this for 3, 2, 1, etc., etc. And because in the problem we have n is less than or equal to 10 to the 5, this is fast enough. We also have another great formula here that I saw some of you use. Even later in the contest, you went back and solved this problem in a different way, which was kind of interesting. And that, of course, is a pyramid angle formula, which is n plus 1, n plus 2, 1. It's an extension of the triangular number formula, but if you just whack n in here, it's actually just going to give you the answer. And there's an infinite number of these formulas, the infinite number of dimensions. If you want to calculate the number of spheres in like a 12th dimensional pyramid. But for this question, this formula and the previous triangular number formula, that's all you need to know.
Okay, because 2 plus 1 is close.
Oh yeah, next is F, flag rotation. So we have a flag. And the flag has cells of different various colors. So maybe the color flag is colored, and we're going to rotate it 90 degrees. So if we were to spin it around, it would look like that. And you have to figure out how many actual cells of this do you need to repaint to get the flag correct. Now, something that you may have noticed, especially with the input that we gave you, is that common squares of colors are preserved between the rotation. So, for example, this 1 by 1 square of white is preserved when we rotate over, as is this 2 by 2 square of red or black, or however you interpret my diagram. And this holds true even if the flag is separated. So, if you have something like this, for example, and you were to rotate it to something like that, these 4 squares would be preserved. These 4 red squares when we rotate it over. So you can use this to derive a formula. Essentially, the number of squares that we don't have to repaint is the sum of the count of some color. No matter where the original stripes of squares are in this flag, when we rotate it, we will be able to rearrange the ones that are kept such that we can form a C times C squared, where C is a count of that color in the original flag. And so the number of colors that we need to repaint by extension is the original size of the input minus those counts. Like count of color, I should say. Square. Yeah, the squares of the count of the colors, you subtract that from the original n squared, and that is the number that you have to retain. Okay, this is a good one. That was a European election, so given some ranked choice ballots, we have to determine a candidate that beats all other candidates. So essentially, given a number of preferential ballots, so we have 1, 2, 3, 2, 1. Take all candidates, we measure them against each other, and if one candidate wins against all the other ones, then they essentially win the election. And the important thing to note about this problem is that this might not actually always be true. It might be true that A beats B, B beats C, and C beats A in like a sort of really rock, paper, scissors arrangement. But we can verify that. Essentially what we can do is we can pre-process all of the ballots, so that all of the information is stored. So given the ballot, we'll essentially define some function where the candidate ID is put in, and it will spit out the rank of the candidate. Now, there's a really nice thing that we can do here. Essentially, if we can compare one candidate against another, and take whoever wins. So, for example, say candidate 1 wins. Then we can get candidate 1 against the third candidate. Then, yeah, candidate 1 might win. And then we can get candidate 1 against the 4 might win. And we can essentially just go through the entire list, sort of constantly replacing the winner. And once you go through all of these, the final winner, the final person, is actually going to be guaranteed to beat all of the other ones. And so this runs in of n times k time, where n is the number of ballots, k is the number of candidates. We just lost enough of this problem. Now there is a horrendous mistake. So you have really screwed up your sum function. You need to calculate the value of sum function sum. However, instead of using the indexes of a loop as like instead of using like I0 to n as the indexes of your loop, you're using the actual values as the indexes. Now the naive solution for this problem is to simply rerun the sum function after every time you update the array. However, this will take n times q time, which in this problem will be too slow. To be fast enough, you really need to be processing every query in O1. However, we can do this with the following algorithm. So we can maintain some sort of count array. Of the initial values of the counts in the array. So this will map a value to the count of the value. And then we can calculate the sum, which is the initial sum. And then say we change some value x to some other value b. What we can do is decrement the count of the old x. So decrement that count in here. We can subtract the old count of that value times the actual value that's situated there, I believe. Just want to make sure I'm right. Yep. So we can denote that as v of x. Plus a of x, where a is like the original array. And then we can add, so we'll subtract all of this, and then add what the new value will be. So we are essentially replacing not only the value itself, but also the value that it was referencing. And then we can add on the new ones. So yeah. Maybe. And then finally, we actually update the value in the array. And so with that algorithm, we can do like some constant time bookkeeping for every update, and we can keep our sum up to date.
I was trying to say, like, break down the sum.
Yeah.
Oh,
So if you were not horrendously mistaken with that question. Oh, intelligence exploration is the next one. So we have arrays, AI, A1, A2, blah, 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 AN, and then we're going to pick some subarray. Some subarray of L to R, then figure out what the implication is. And we have some very specific implication rules, which I will write down here. And yes, that is that 0, 1 to 0 is 1. 0 onto 1 is 1. 1 onto 0 is 0. And 1 onto 1 is 1. Now, there are a couple of observations you can make here. The first one is that if the right value is one, then the output is going to be one.
I was saying.
Yeah, well, we consider what is
It's just if there's.
That's very useful. The other observation you can make is that if you have some array of alternating zeros and ones, then the value, once you evaluate that array, if you have an array of just zeros, then the value of that array, once you do all the implications, is going to alternate between 0 and 1. So for example, 0 onto 0 is 1, 0 onto 0 onto 0 is the same as 1 onto 0, which is 0. But then 0 onto 0 onto 0 onto 0 is the same as 1 onto 0 onto 0, which is the same as 0 onto 0, which is 1. So you can see when there's 2 of them, it's 1, when there's 3 of them, it's 0, when 4 of them, it's 1, so on and so forth. So it'll alternate between 0 and 1 depending on the parity. Yeah, so for each position, you can pre-compute the index of the last one appearing not after it. And that way you can determine the number of zeros in the end of a subarray in like a one time for any given subarray that you're given. And that is like O of n plus q time. So essentially when you were given some subarray, you can already know how many zeros are in the subsets, you can evaluate the zeros, and then complete by just evaluating the rest manually. That's n plus q time. Fun one. Oh, does anyone want to do the solution for A? I know there was a lot of try ones.
It's John's idea.
So we constructed a trie, and then we find the longest path between two terminal nodes.
So can you explain what a trie is and sort of how all that works?
The trie is like a prefix tree of all the words that you are like constructed based on the prefix letters, and then once it's branched out, we will like find the maximum depth of the nodes, and then we will DFS on that deepest node in order to find the longest other terminal ends, and that ends will be the length of the different after we delete the prefix of the two word.
Yeah, they keep the two longest words as some terminal node and use that to calculate the length of the resulting one. That's pretty good. There was another solution here that I didn't see anyone do, but I think this is pretty good. And so the claim I'm going to make is that given a pair S and T and a third word V, we should always replace one of the words S and P with a V, and it will give at least as good of an answer, if not better. And this is actually very interesting. So say we define the goodness of S and P as the length of S plus the length of T, minus the goodness of, minus their longest common prefix, which we are going to define as this function P. Then this is proof by contradiction. So let's assume that G of S and T is actually better than G of some V and S. And also that it's better than some G of V and T. Remember, the length of V is longer than the length of T, and the length of V is longer than the length of S. Let's just take this relation here. This implies that the length of S plus the length of T minus PST is less than the length of V plus the length of S minus P of V and S. These are common, so we can cancel them. Oh, yeah, we subtract two PST because, then we subtract the prefix from T and the prefix from S. So this should be a 2, this should be a 2. And this would imply that the length of T minus 2P ST is less than the length of V minus 2 PS. And this implies that, what is this? Just the length of S is the thing that kind of SNT. So this is the relation you derive. We essentially say that the length of the prefix SV is longer than the length of the prefix ST. However, that was just with this relation. With this relation too, we find that the prefix of VT is greater than the prefix of ST. This is a contradiction because if the largest common prefix between SV is bigger than the largest common prefix of ST, and the largest common prefix of VT is larger than the largest common prefix of ST. This is not possible because we expect ST to at least have one of these two things. Either the largest common prefix of ST will be in VT because V is longer, or this one will be inside of VT because VT is longer. And by contradiction, we know that G of ST cannot be greater than G of VS. That means the one with the longer value, at least one of these relations with a longer value must be correct. And this implies that the longest word has to be part of our answer. And so once we know that the longest word has to be part of our answer, we can simply check it with all of the other words in a brute force manner to derive the
We just assume. We just assume.
That's a pretty tricky one. People to derive it in contest.
Yes, but I just don't feel like it's because that when we go out. Always reach the longest value.
Whatever. Like, I think it's pretty simple. Yeah.
Does anyone want to explain jailbreak? Actually, it's pretty trivial. It's just a very annoying DFS. You got to figure out from what rooms you can access what other rooms. The hardest part is actually just figuring out how to pass the input correctly. Made a lot of people very angry. I agree, it is a bit of a strange problem. It's very similar to the one you see in like admin of code. They have but yeah, it's a bit of a strange one. You can use a for loop in both directions to essentially determine which cells can access a ladder, and then define the graph.
So, yeah. Yeah.
Does anyone have a solution for C?
This over to.
So on you, I think C is sort of where I started getting a bit beyond my pay grade. But I can read out at least what they're thinking here. So given the two types of penalty times for n teams, we're going to find out all the ways of choosing the type of penalty time for each team, so that and the number of fixed points that the score point contains in total. So the fixed points is I believe it's where the penalty matches are ranked.
Yes.
Yeah. Yeah, so given the last submit time and the sum of submit times for each team, figure out the sum of the number of fixed points over all of the ways that we can choose penalties. So we can either choose for it to be loss of bid time or sum of the bid time. We essentially choose one of two values for the teams, or any of the teams, or any for all of the teams. We choose between these two choices, and so there's 2 to the n possible options. Instead of finding the fixed point for each of the 2 to the n options, we can find the number of times that team I is the fixed point. And so we can loop over all the team and try both of the options for the penalties at the potential fixed point for team I, and call this potential fixed point F. And so the other teams form 2 groups. So there's what's it say here? A, where teams of one scoring strategy, which they denote as LJ, I assume L is last submission, is less than F, and SJ, which is less than F. Teams where it's in between, and teams where it's above. And so the number of ways to choose the L submission times for team I to have a fixed point at rank F is apparently 2A plus B.
Literally because he. 2 hours. 2 hours to go to this hotel.
So B to.
What?
Right, so it's 2 to the number of teams that are guaranteed to be above, plus the number of teams that are guaranteed to be below, plus the combination of teams that can be in the middle. And by filling the arrays, we can find more absolute A, absolute B with binding set. Yeah?
What's the bottom under B?
Oh, it's F minus like A, or the number of A. Where F is like the actual fixed point itself. About point.
So would this one include both considering I as the sum and considering I as the minimum, like the lowest, like the time between time of last submission?
I believe you'd have to do it for each one.
Okay, so you use the same thing for.
Yeah, so you'd have to compute it for if we're using L for the particular team and if we're using J for the particular team. And there's a bunch of inverse factorial stuff to make sure that you don't go over the much. Hi, Ruben.
There were some people who were in the waiting room for the last 10, 15 minutes.
Oh no.
Basically, you can admit them from the panel, but I did cut him down.
Okay.
Yeah. How are we doing?
I ran out of people to give editorials, and we're at K. Yeah, because this one is a bunch of mod stuff. Not really sure how it works. We don't have anyone that can explain it.
Okay. You want to go?
Yeah, sure. I appreciate that.
Sure.
It is like kind of intuitive, but not enough that I could actually explain it well, I think.
Sure.
So this is the
The kangaroo is on the spot, guys.
Yeah, absolutely can.
Oh, and it like jumps.
It
like
it goes to like buttons. Yeah.
Sure. That's it, right? Okay.
Yeah.
Okay, cool.
Yeah, okay.
So if the kangaroo is at position Y, then it's pretty bad. I think I have some better ones.
Okay.
So if the kangaroo is at position Y, it then jumps ahead Y times Y minus 1. Also, are we in frame? Is the board in frame?
Yeah.
So it's at Y, it then jumps ahead by Y times Y minus 1. Of course, this is just Y squared. This means that the first move takes the kangaroo from X
to x squared. The second move squares again to x to the 4, then again to x to the 8, and so on. And we want to know when this reaches square number 1, modulo n. So all of these squares are taken modulo n. So we want to know what is the smallest solution. What is the smallest I such that x to the power of 2 to the power I is 1 mod n.
Oh, apparently they're just getting a static image from the room with the camera on rather than the video. So it is in frame but not moving. And that actually makes sense because Rory's face is still there.
Oh, that's pretty bad.
Yeah.
Are you getting audio?
Yeah, we're getting audio at least.
Oh, okay, all right, cool.
We can maybe just
gonna go and restart the video. Did that fix anything? Doesn't seem to have.
oh man.
Nope, it's the exact same frame as before.
Beautiful. Oh man.
That's not ideal.
I could just give them the FTP.
I'm just gonna leave and rejoin from the room.
Yeah. Actually record this call.
Testing.
Oh no, oh we are like alive.
Oh, that's better. It's better.
Awesome.
I like this.
So where were we? We had that if we are at position y, we jump forward by y times y minus 1. So in other words, we go to y squared. So we start at x, we then go to x squared, then apply the same operation, so we go to x to the 4, apply the same operation, so we go to x to the 8, etc. And at every step, we're taking the result modulo n because we wrap around. Yeah. Cool. So we want to know what is the smallest I such that x to the power of 2 to the power I is 1 modulo n. All right. Now, we do not want to just try i's in this, right? We don't want to just keep going forever because the concern is what happens if like this takes like, I don't know, a billion steps to get back to 1, right? However, this doesn't happen is, I believe, the key thing. Yep. Cool. So R is less than or equal to N. What is R? R is not a thing in this, right? Okay. I think I know this.
Oh,
I have no idea, man.
Or inverse modulo.
But yeah, can I see the original size?
It needs to be a prime.
That's this, right?
I mean, what's the name?
Yeah. As in, like, we haven't renamed any like variables.
No.
I think that's the key. Yeah, I was thinking about something like that.
I think I know.
Yeah.
Right. So the concern here might be what happens if we have to try lots and lots of values of I here before we ever get back to 1. However, this never happens because of some properties of modular arithmetic, which is that if x and I don't share a common factor, then we are guaranteed to get back to 1 sooner rather than later, right? Specifically, can I answer?
Do you mean X and N rather than X?
X and N, yeah, thank you, yeah. Yep, okay, spin. Whoa. It's gonna flip the tab.
Yeah.
That's not something.
How should I? And I would not.
So X and N are here, like could have fun, right? But that's still fun.
Yeah.
Yeah, okay, cool. So the key result we're going to use here is that so is Euler's theorem that x to the power of torsion of n is 1 mod n, and this torsion function phi is the number of numbers up to n that are co-prime with n, so it's always less than n, right? So certainly if I take any higher power than this, it should hang on. So
Yeah. Sure. Therefore, any I. That doesn't help at all. That's right. The answer can be
Oh, yeah, it can be.
Oh, okay. I think I know. Alright. Sorry, folks, I am making this up as I go along, so forgive me for saying things that are not entirely correct. Okay, so we wanted x to the power of 2 to the I to be 1 mod n. Right. And so the question is like, yes, so if x and n have any common factors, then we are doomed, right? We're never going to get back to 1 because that common factor is never going to go away from repeated multiplying, exponentiating in, right? If GCD of x and n is more than 1, then it is certainly impossible. That's guaranteed, right? Let's suppose otherwise. So if the GCD is equal to 1, if they're co-prime, all right, so for this to work, then if they're co-prime, then yeah. Okay. Fine. Let R be the order mod n of x, i.e. smallest z such that x to the power z is 1 mod n. Yeah. So the smallest power of x that I need to get, the smallest power that I need to raise x to get back to 1 mod n. This is called the order. Yeah. Cool. I can guarantee that. So I can guarantee 2 things. One is that this power 2 to the I has to be a multiple of that R, right? Because if it's not, then I take some whole number of steps of x to the R, x to the R, x to the R, and then I have a bit left over, which is not 1 by the definition of the order, right? So it's definitely R divides evenly into 2 to the power I. In other words, R is itself a power of 2.
Oh, and you only need to take so many of those.
Yeah. Yep. However, we also have the fact that this order R can't be very big either. It can't be more than n. Yeah. To see why this is, suppose that the order R was actually bigger than n, right? If x to the R, if R was bigger than n, that means that among the first n many powers, x to the 0, x to the 1, x to the 2, x to the 3, all the way up to x to the n minus 1, if none of these are 1, then by the pigeonhole principle, 2 of them must be the same. And so you have x to the a and x to the b, but they're both the same value, and therefore x to the a minus b, or b minus a, whichever one is bigger, will be 1, and that thing is less than n, so that contradicts the minimality of R. Yep. So this leads to a contradiction as well, and therefore R is, well, actually strict less than n. Yep. And therefore, if there is all we have to check is values of 2 to the I that are multiples of values R, which are powers of 2. Oh, sorry, let me put that differently. We only have to check 2 to the I, which is a multiple of something that is a power up to n. And therefore, the two PIs that we have to check are themselves only up to n, i.e. the i's that we have to check have only log many values, so 60 such 60-ish values, because that's a log base 2 of 10 to the 18. Yeah.
I said 60, yeah.
Yeah, cool. That is at least 4 strokes. So
No, that's very well reason. Thank you.
I hope that was helpful.
No,
Sorry, it took me a couple of guys to get that.
no, for making enough as you're going along, that was fantastic. I think I can probably read about G, which is our last problem.
Okay, that's.
So G is an interactive problem. We want to navigate wormholes to find an ancient relic without running out of fuel. Now we actually know where the wormholes are at the start of the problem. Yes, and we start at point 1, which is our home base. Whenever we go back home, we can refuel. And we want to get to point N without running out of fuel. And the wormholes will take us to some other wormhole, but we don't know exactly which wormhole it will take us to until we try. So that's what the interactive part is. And so you can definitely, like, the observation we make here is that you can refuel more than enough times to simply explore all the wormholes until you find a way to reach the relic. This is because, yes, the shortest travel distance from point 1 to any other point is at most d on 2. So it'll take at most half of your fuel to get to any given point. And I believe there's a limit on the number of times we can refuel. Yes, refueling more than n on 2 times will result in a wrong answer. So in this case, we can actually explore every point until we find a way to reach the relic. So we can perform like a sort of live search. So we can explore the wormholes while always keeping enough fuel to go back to home base. Once we travel a wormhole, we can figure out whether we can go to some other wormhole and then back again. Once we travel through a wormhole, we can immediately just go back to the entry point. So we will be able to know this ahead of time. So if you can reach the relic within the fuel limit, then you just do that. Otherwise, you can go to the closest wormhole that we haven't explored yet. We can do this using Dijkstra's algorithm or Floyd-Warshall. And if we can still reach like another wormhole while having enough fuel to go back to the base, then yes, we can go to that wormhole and then go back. Otherwise, we do want to go back to the base to refuel and then essentially repeat. In the worst case, we can explore all the wormholes in 2 on n runs, which is the number of limits we have on refueling. So that is all good. Essentially, just a Dijkstra's algorithm where you have to return back to home base without running out of fuel. And then once we know the way, we can just follow the optimal path. So the time complexity of this is n cubed or n cubed log n, depending on how you implement your search. Or there are some more clever solutions that do n squared and n squared log n. We can do some clever caching. And that's it. Any questions about any of the problems? Yes, but some jitter.
No, that was from long ago.
Yeah. What the chat there? Oh. There's one main thing I want to know. How many of these problems are previous ICPC problems? Is it all of them or some of them? These are all problems from some ICPC preliminary finals or practice contests. I believe this one was the freshman programming contest, which is just like a ICPC practice that is run in. Oh, where is it?
It's in Delft.
Delft. Oh yeah. It's in Delft. That's right. So yeah, they always come from either some ICPC official contest, some ICPC practice contest, some regional finals, preliminary finals. We usually do like preliminary and regional finals from the sort of Asia Pacific region. But in this case, we took from yeah. Okay. Any other questions? Okay. Thank you for coming. I hope you learned something from this contest. Hope you learned something from this editorial. I hope the questions were actually game. Right. And yeah, if you have any other questions about the problems, you can look at the FCP 2020.
Like there's a wizard in here and there's a wizard not, and the visit only visited passes on G, and we have like 15 wrong submittals.